Hello everyone, welcome back to MAT052. This time I'm just going to go over how to find critical values from the problem settings that we're used to seeing. So we've got confidence intervals, and we'll be given some confidence level, and then we have to go find the critical value Z alpha over 2 for confidence intervals. As well as in hypothesis testing, not directly where we do these critical values, but if we're doing, testing hypothesis test by region, we'll need to know left-tailed, right-tailed, two-tailed to plot the values of the critical values Z alpha over 2, Z alpha, negative Z alpha, and just go through that. So I'm going to step through that procedure, and let's get started. So I'm going to turn my camera around here and get it going down so that we can see it. Okay, let me see. Once more. There you go. So critical values. Critical values are used in both confidence intervals and hypothesis testing. In confidence intervals, we use the critical values directly. That's what I'm saying. And they are always in the form Z alpha over 2. So they will be in the margin of error formula, and it'll be the Z alpha over 2 that we have to come up with. So in hypothesis testing, we use critical values indirectly as a way to separate the H0, the null hypothesis rejection region, from the H0 failed to reject region. In this case, the critical value form is determined from H1 as a left-tailed, right-tailed, or two-tailed, and is shown. Okay, so the negative Z alpha, Z alpha, Z alpha over 2. So when we're doing confidence intervals, we are always doing this confidence intervals where it shows up in the margin of error, and it all depends. The margin of error formula always depends on what we're trying to build a confidence level for, a confidence interval for. And then just the details within it. Do I know the standard deviation? Do I know the population standard deviation? Do I have to use the sample standard deviation? So for Z alpha over 2, what we're looking for is the normal distribution. And I'm looking, when I go to the back of my book using the margin of error formula, this is how a confidence interval is built: minus X bar minus Z alpha over 2. Population standard deviation sigma divided by the square root of n less than mu, the mean, the population mean, and then on the other side, the X bar plus this margin of error. Okay, so this is always, we're looking at something like X bar plus or minus the margin of error. And that margin of error is built up of two things: the critical value, and then we're going to multiply it times the standard error. Okay, so that's kind of what we want to look at, is building this. And in this case, what we're looking at in this time is always Z alpha over 2. We're going to do next time, we're going to do the student's T distribution, and we'll look at things like T alpha over 2. I'm going to open this up just a little bit for us there. Okay. So we would just want to go through and pick that up. Here's another confidence interval for proportion. Also shows up as using Z alpha over 2, P hat 1 minus P hat over N. This is the standard error piece of it. And here's the Z alpha over 2. That's the critical value that we're using. Notice that this is given when we're doing with this formula. If I want to construct a sample size, I still have to do the Z alpha over 2. This shows up here. P hat, if I'm doing this thing, this is the form where if I knew a previous study of P hat, I use it. And if I don't use it, this is going to be 0.5, I assume, and then 1 minus 0.5 is just 0.5. The 0.5 times 0.5 is going to be the 0.25. So what is alpha? How do we get that alpha thing going on? Okay, so here's a quick picture. Confidence intervals always look at this one picture here. Okay, so it basically has a picture of always I've got this bell-shaped curve, and I've got two tails here. This tail out here, the left tail, and the right tail. This is the same thing that we call two-tailed if we're doing hypothesis testing. So this is what we're concerned with, and this is minus Z alpha over 2, Z alpha over 2. It's symmetric, so if we use some area here or this one to the right, area to the left, it's going to give us that same value of Z. And in the formulas, we're always assuming the positive values when we're doing those. Okay, so inside, there's always some confidence. So like, let's say if we did, say 98% confidence, this is 0.98, the area is 0.98 in the inside, and my alpha, this is my standard way of working it through. Alpha is going to be my 1 minus C, so it's 1 minus whatever the C value is, the confidence value. Let's say if we're going to do 0.98, here's 0.02, but 0.02 outside, all outside. And here it's evenly distributed among these tails for confidence intervals and two-tailed tests. This, we just divide whatever that alpha is by 2. So if I divide 0.02 by 2, I get 0.01 area here, and 0.01 area down there. And that separates our confidence inside and then our tails on the outside. So that's how we go about working on our alpha level. So getting alpha from the confidence level, here's a couple of examples I did for a 80% confidence. For 80% confidence, 80%. And if I go quickly, I'll draw my picture. I'll say 80 on the inside, which is 0.08. So my alpha is just 1 minus 0.8, and that's going to be 0.2. And then this little filled in area is alpha over 2, alpha over 2. So my alpha over 2 is the 0.2, and that's just going to be 0.1. If I did this very same thing, I keep doing the very same thing. If I'm going to talk about 90%, this was for 90%, 80% confidence. Here's 90% confidence interval. Same thing, a little tail, I just draw that with a little blocked in. Here is 90% or 0.90. My alpha is going to be just 1 minus that. That's 0.10 outside, but it's evenly distributed here. So the alpha over 2 is the 0.10 over 2, which is 0.05. And that's going to be the very same thing. So it's 0.05 to the left, 0.05 to the right. If I'm going to use this number here, I need to go 1 minus 0.05, which is 0.95 to the left. I'm just looking at that critical value that's going to separate 0.05 to the right to 0.95 to the left. I could also go here, recognizing that this is going to be a negative number, and then just use the positive number because it's symmetric. This with 0.05 to the left and that number to the right is just going to be a positive and a negative number. Okay. So here's the format of the normal distribution table. Let me put me down in the corner here. So here's the format of the normal distribution table. When you go in here and you go to table 8.2 in the back of the book, it's always area to the left. It says area and it's got a little picture, and that means the area is to the left. And here is, if we're going to do critical values, I'm looking for alpha over 2 in here. In the body of these tables, that's the probability or the area to the left. And then here's the z-score, the first two numbers, and then to here. So this is good to 2 decimal places or the 100th position. And I just go find that and then report like negative 3.2, negative 3.6, 1 or 2. Okay. So let's go and kind of look at some of these things if we just did it in the table. So for an 88% confidence level, we kind of did this a while ago. We go through and I find out alpha is 1 minus C. There's the 0.80 on the inside. That's in the tails left is 0.20, and I need alpha over 2, half of it on the left, half of it on the right. So I'm going to go here and I'm going to find the closest number I can come up with 0.10, and that looks like it's going to be about the closest one. This is just kind of what we need for here, and that would give us the negative. When we're reading here is negative 1.28, but I'm going to use the positive version, because if I came here, let me pull this back up. Here was the 80%, so now I know the critical value right there, that is negative 1.28, but I know it's going to be symmetric, so all I have to do is just say here's going to be the plus 1.28. It's symmetric, half of it's 50, that's my 0 point, half 50, 0.50 to the right, 0.50 area to the left, and all of these things are going to be symmetric in there. Here's another example I just did for the 90%. So we're going to do the very same thing. I did the 0.10, half of that, 0.05, that's my alpha over 2 value. And now I'm going to go through and I'll move this down a little bit. So we're just going to keep going and going. And the closest thing I can get to 0.05, here's kind of the two things that are just 5 apart. And I'm going to go 1.65. I'll go with the biggest one. So that'll open up my confidence interval just a little bigger. You can also do this, but with technology, given, like a TI-84, the 36 will also do these. So that's kind of the standard way for confidence intervals. And what about if I'm doing hypothesis testing? So for confidence intervals, I'm always wanting to do this alpha over 2. If I'm doing hypothesis testing, we're not given confidence, we're just given directly this alpha level. Okay, so the alpha is either for setting up regions, so I've got a fail to reject region. Let's pull that up again. Pull this out. Open this up a little bit. So here, when I'm doing hypothesis testing, I'm doing regions, so let's just do a left-tailed region. So I've got something like H1 is going to be mu less than 100. Okay, so this, when I go through it, I'm going to say that's a left-tailed test, and they'll say do it at the alpha 0.05 level. So here the full alpha for a single tail, that area in there is going to be 0.05. If I was going to do the two-tailed, then I need to split it by 2. And then I need to find that critical value that separates anything to the left of here. That's the rejection region. And I'm rejecting, if my test statistic falls in that, then I reject H0. Here is the fail to reject. And any test statistic in there, we fail to reject H0. Okay. So that's what we're looking for when we're doing hypothesis testing. They're always giving us what level we're going to test at. So here, all I have to do is do the critical regions. Here's this for the left. I'm expecting a negative value for critical, and here's the two-tail. So I'm looking at H0 equal versus H0 not equal. That's for the two-tail, and here's H1 being greater, mu greater than some number, or P being greater than some number. And here I'm expecting a positive value for Z alpha. So let's look at some of these things. If I did a left-tailed, so here would be the left-tailed version, and I'm given 0.05. I want to test at that 0.05 level. I just want to go here. The area's to the left, so that's directly in here. I just need to find that 0.05. Either one of these, and again, I'm going to do the 1.65, 1.65, where those two cross. That's the closest, that both of those are only 0.0005 apart. And if I added 5 here, I would get the 0.050, subtract it, I'd get but I'm going to use this negative 1.65. Why negative? Because I'm looking at a left tail. This needs to be a negative number. Here again, right now that hump is 0. What about a right-tailed? We'll just do the picture over again. Here's my bell-shaped curve. There's my right-tailed. So from H1 being something like whatever it is that we're measuring, mu p, let's just put it this way, mu p is the 2 that we're going to get from here being greater than some number. Then that means we're going to do a right tail test. And this points to the right, so we do a right tail. And I just need to go find that number. And again, this is going to be, if I go back down here, that gives us a 1.65. Positive version, because here would be 0. We wouldn't want to plot a negative number out here. And again, this is fail to reject region. There's my rejection region, and the area inside is the full alpha of 0.05. So that was just some of the basics for the normal distribution. We can go through, let me kind of go back. I wanted to look at one other thing real quick. Here is your work for this week. Some problems. Let me load this up. I'll show you what this looks like. So here I'm giving you a couple of different scenarios. And I just want you to go to the table. So here it is. It's like finding confidence intervals here. So I put 2 tails, so it would be the same thing whether you're doing, a confidence interval or a hypothesis test. But here's confidence intervals because I'm giving you the confidence, 90% confidence, 95. So you need to find alpha, 1 minus 0.90, 1 minus 0.95, because this would be something like, for the mean, sigma known. So you would be using Z scores. Okay. Find the critical value that separates the rejection region and failed to reject region for a left-tailed hypothesis test. Left-tails lets you know whether you're going to be a negative or a positive. And here's the alpha. You'll get the full alpha at this, 1.10. And again, this would be used if you were looking for something, doing a hypothesis test for the mean. The sigma was known, so that would be a z-test statistic. And you always would be doing the test statistic, comparing them to those regions. So this is just giving you those regions, and we'll look at p-values next time as we go through next week. Okay, and then finally do a 2-tailed version. Right tail is positive. Here I need 2 values for a 2-tailed, a negative and a positive with that alpha value. Okay, so hopefully that'll get you started. So work on these things. There's only a couple of them, and get them turned in, and we'll see you next tape.